Welcome to the hydraulic system lesson in the PMDG 737 Next Generation Groundwork from Angle of Attack. This lesson will cover the following topics. We'll start with an overview of the general principles behind hydraulic systems. We'll run through an overview of the hydraulic system on the 737 Next Generation. Then we'll discuss hydraulic systems A and B, systems A and B fluid leaks, the power transfer unit, the standby hydraulic system fluid leaks, and a lesson summary. The hydraulic system on the 737 powers many components, and we'll be elaborating on the specifics later in the lesson. Aircraft hydraulic systems are used to move control surfaces or other equipment, such as the landing gear, which are too heavy to be moved by muscle power alone. Hydraulic systems vary hugely in complexity from aircraft to aircraft, but they all revolve around one basic principle, Pascal's law. Pascal's law states that when pressure is applied to an uncompressible fluid in an enclosed container, pressure is transmitted throughout the fluid undiminished and acts equally upon every part of the container. To illustrate this, let's look at a container with two pistons of equal size. This is the simplest type of hydraulic system possible. If a force is exerted on the first piston, it will apply pressure on the fluid, which will be transmitted through to the second piston. Because the two pistons have the same surface area, the force exerted by the second piston will be exactly the same as the force that we applied to the first piston. This means that if we apply a 5 Newton force to the first piston, we'll get a 5 Newton force from the second. Let's take a look at what happens if we increase the size of the second piston. The surface area of each piston is crucial here. Let's give the first piston a 1 meter square surface area and the second piston a 5 meter square surface area. The equation we need to keep in mind is force equals pressure times area. This means that the pressure transmitted through the liquid varies as a function of the force that we apply to the first cylinder. So if we apply a 5 Newton force to the first cylinder, it will create a 5 Pascal pressure in the liquid. Remember that according to Pascal's law, the pressure will remain the same throughout the container. This means that the liquid will exert a 5 Pascal pressure on the base of piston number 2. Force equals pressure times area, so given the 5 meter square surface area of the second piston, we'll get a 25 Newton force from it. This means that piston number 2 has exerted a force 5 times larger than the one we initially applied to the first piston. This is why hydraulics are so useful. They allow us to multiply forces and apply them to control surfaces and other equipment that would otherwise be far too heavy to move. Let's put this into context and look at a very simplified animation of hydraulics moving an elevator. This is a very generalized diagram and is not intended to reflect the architecture on the 737. It's just to put all this physics and maths into context before we move on to talking about the 737 hydraulic system. This diagram depicts an aircraft elevator actuated by a single piston. A selector valve rotates through 90 degrees to route hydraulic fluid either side of the piston head to move it back and forth. To pitch the aircraft up, the aircraft pulls back on the control column and the elevator will move up accordingly. When the control column is moved back, the hydraulic fluid is pumped under pressure into the actuating cylinder, forcing the piston backwards and lifting the elevator. When the control column is moved forward, the selector valve directs the fluid onto the other side of the piston, pushing it forward and moving the elevator down. Because the piston has a large surface area, it exerts a large force on the elevator mechanism, enabling the elevator to be moved even when the aircraft is flying fast and there is a high airflow over the control surface. The 737 Next Generation has 3 hydraulic systems: System A, System B, and the standby system. Many systems on the aircraft use hydraulic power as their primary, and in some cases sole means of actuation. The A and B hydraulic systems together power the following aircraft systems: flight controls, leading edge flaps and slats, trailing edge flaps, the landing gear, wheel brakes, nose wheel steering, thrust reversers, and the 2 autopilots. There are some pretty vital systems in that list, which is why we have 2 main hydraulic systems. This gives us system redundancy and with that comes greater safety. The standby hydraulic system is a further backup that is available in the event that either system A or B pressure is lost. Systems A and B are the two main hydraulic systems on the 737. They are independent systems, yet power many of the same components. There are several components that are only powered by one of the two systems, however, so it is important to know which components are covered by which hydraulic system. Hydraulic system A powers the following components: the ailerons, elevator and elevator field, the main rudder power control unit, two flight spoilers on each wing, the ground spoilers, alternate brakes, the engine number 1 thrust reverser, autopilot A, normal nose wheel steering, the landing gear, and the power transfer unit motor. Hydraulic system B also supplies power to the ailerons, elevator and elevator field, and the main rudder power control unit, but the list changes a little from there on. System B also powers the two remaining flight spoilers on each wing, the main yaw damper, leading edge flaps and slats, trailing edge flaps, normal brakes, the engine number 2 thrust reverser, autopilot B, alternate nose wheel steering, the landing gear via the landing gear transfer unit, and the power transfer unit pump. The landing gear transfer unit is covered in the landing gear and brakes lesson, and we will be discussing the power transfer unit in detail later in this lesson. The hydraulic systems on the 737 Next Generation use BMS 3-11 Type 4 or 5 hydraulic fluid. The two types are interchangeable. BMS stands for Boeing Material Specification, which sets out guidelines for various standards that the fluid must meet. The hydraulic fluid is fire and erosion resistant, but isn't pleasant if spilled. Each hydraulic system has a reservoir that supplies hydraulic fluid under pressure to the hydraulic pumps. The hydraulic reservoirs are easily the most conspicuous pieces of equipment in the main landing gear wheel well, and they're located on the forward bulkhead. The reservoir center aft in the wheel well is for the standby hydraulic system, and we'll be discussing that later. The System B reservoir is considerably larger than the System A reservoir, and this is clear when looking at it in the wheel well. System A reservoir volume capacity is about 6.8 gallons, and System B reservoir volume capacity is about 10.7 gallons. Each reservoir is pressurized by bleed air from the engines or the APU. The bleed air supplies a constant pressure of approximately 45 to 50 psi to the reservoirs, which ensures a positive pressure to the hydraulic pumps. If the bleed air switches on the forward overhead panel are selected off, then there will be no flow of air to the reservoirs to pressurize them. This is of course normal during a bleeds-off takeoff, and the hydraulic pumps can still function without bleed air pressure at low altitudes. Reservoir pressurization is there primarily for high-altitude flight, where the atmospheric is not sufficient to prevent foaming and cavitation in the pumps. Each hydraulic system has two pumps, an engine-driven pump and an AC electric motor-driven pump. The System A engine-driven pump is powered by the number 1 engine, and the System B engine-driven pump is powered by the number 2 engine. The two AC electric motor-driven pumps are located on the forward bulkhead of the wheel well. The purpose of the engine-driven and electric pumps is to supply pressure to the hydraulic systems. In summary, to differentiate the two types of pressurization going on here, bleed air pressurizes the reservoirs, which then supply hydraulic fluid to the pumps. The pumps then pressurize the rest of the hydraulic system. The System A reservoir has a standpipe for the engine-driven pump, and a port in the bottom of the reservoir for the electric pump. The System B reservoir supplies its engine-driven and electric pumps from the same standpipe. A port at the bottom of the System B reservoir supplies fluid to the power transfer unit, which we will be discussing later in the lesson. There is a shut-off valve between each reservoir and its respective engine-driven pump that is triggered by pulling the corresponding engine fire switch. This valve shuts off hydraulic fluid flow from the reservoir to the engine-driven pump. All four pumps supply approximately the same pressure to the hydraulic system, but the engine-driven pumps are much more powerful and put out approximately 4 times more volume than the electric pumps. The engine-driven pumps are rated at 36 gallons per minute at 3000 psi, and the electric pumps are rated at 5.7 gallons per minute at 2700 psi. Output pressure from the pumps is maintained at a constant pressure, regardless of system demand. The more demand there is on the hydraulic system, the greater the fuel flow required to maintain that constant pressure. A pressure compensator in each pump controls the fluid flow to maintain hydraulic pressure as demand fluctuates. Once pressurized by the pumps, the hydraulic fluid is filtered and flows onwards throughout the rest of the system. As there is only a finite amount of hydraulic fluid, each system that uses hydraulic power returns the fluid to the reservoirs. The fluid is filtered by return filter modules before it goes back to the reservoirs. Controls for the 4 hydraulic pumps are located on the forward overhead panel. There are 2 pairs of switches, a pair for the A pumps and a pair for the B pumps. These are simple on-off switches. The engine-driven pumps are attached to the accessory gearbox on each engine, so they never actually stop spinning, regardless of switch position. When the engine hydraulic pump switches are selected off, a solenoid valve closes and stops the pumps from transmitting pressure to the rest of the system. Because the engine-driven pumps are mounted on the accessory gearbox, there is no need to select the engine pump switches off on shutdown. It is actually advised to leave the engine pump switches on during shutdown to prolong the life of the solenoid valve. The electric hydraulic pump switches simply provide and remove power to the electric pumps. We don't want to turn this into a lesson on the electrical system, but it's important to understand how each pump gets its electrical power and how that provides further redundancy for the hydraulic system. The electrical system has 2 AC transfer buses, which in flight usually receive power from the integrated drive generators on the engines. Engine number 1 powers AC transfer bus 1, and engine number 2 powers AC transfer bus 2. Engine 1 also drives the system A engine-driven pump, and engine 2 drives the system B engine-driven pump. AC transfer bus 1 powers the system B electric pump, and AC transfer bus 2 powers the system A electric pump. This crossing of the power sources to the 2 main hydraulic systems ensures that hydraulic pressure will be maintained with the loss of either engine or either AC transfer bus. The hydraulic fluid is cooled by heat exchangers in the main fuel tanks. System A hydraulic fluid is cooled by a heat exchanger in main tank number 1, and System B hydraulic fluid is cooled by a heat exchanger in main tank number 2. Only some of the fluid in each system is passed through the heat exchanger as it passes around the loop. Each pump has 2 outputs, an output pressure line and a case drain line. The output pressure line does as the name suggests. It pressurizes and provides fluid to the rest of the hydraulic system. The case drain line drains a smaller quantity of hydraulic fluid away to be filtered and cooled. It is this case drain fluid that passes through the heat exchangers in the 2 main fuel tanks. Heat flows from hot to cold, so the heat exchanger transfers heat from the hot hydraulic fluid to the cold fuel in the tank. The fluid is then routed back into the reservoirs. The electric pumps generate a lot of heat and are cooled by hydraulic fluid passing through them. Because the electric pumps rely on the heat exchange process in the fuel tanks to keep cool, they should not be run on the ground if there is less than 1,675 pounds of fuel in the related tank. Despite the cooling system in place for the electric pumps, there is still potential for overheating. Temperature switches downstream of the electric pumps in the case drain line monitor the hydraulic fluid for overheat. The amber overheat lights above each electric pump switch illuminate when these sensors detect an overheat condition. Note that there are no overheat lights for the engine-driven pumps. This is because overheat situations are much less of an issue for the engine-driven pumps. The engine pumps are mechanically driven by the accessory gearbox on each engine, so the heat produced is negligible. The AC motors on the electric pumps produce a lot of heat by comparison, so the overheat warning system provides alerts to the flight crew when an overheat condition is sensed, but only for the electric pumps. All 4 hydraulic pump switches have low pressure lights. Each pump has a pressure switch downstream, which is tripped when pump output pressure decreases to less than 1300 psi. This triggers the related low pressure light. When an engine fire switch is pulled, the related engine-driven pump's low pressure light is deactivated. It is a given that the pump will be putting out low pressure when the fire switch is pulled, as the engine will be shut down immediately. Crew workload is high following an engine shutdown, so the light is deactivated to eliminate the unnecessary distraction it could cause the flight crew. If the hydraulic reservoirs are not properly pressurized by bleed air, foaming may occur at high altitudes, causing pressure fluctuations. Such pressure fluctuations may cause the blinking of the related low pressure lights. Any of the low pressure lights will trigger a master caution and the hydraulic light on the first officer's system annunciator panel. There are also hydraulic system indications on the lower display unit systems display. Quantity and pressure for systems A and B are shown at the top of the display. Quantity is expressed as a percentage of the normal full level, 5.7 gallons for the A reservoir and 8.2 gallons for the B reservoir. The percentage range extends up to 106% to indicate an overfill of the reservoir, and if the quantity dips as low as 76% or below, a white RF or refill indication appears beside the related quantity indication. The refill indication is inhibited in flight and appears only when the aircraft is on the ground with either the flaps retracted or both engines shut down. Fluid quantity is determined by a simple float and transmitter in each reservoir. The float rises and falls as quantity changes and pivots around the transmitter body. The transmitter then forwards the quantity signal onwards to the indications on the system's display. Expect to see some variations in quantity throughout normal operations. The most noticeable momentary quantity variations occur when the landing gear or leading edge devices are being actuated, as they place great demand on the hydraulic system. A lot of fluid flow is therefore required to maintain rated pressure. This causes a temporary reduction in quantity indication. A longer-term reduction in quantity may be observed during long periods of cruise where cold soaking occurs in the system. As the hydraulic fluid cools, its volume decreases, causing a decrease in the indicated quantity. Hydraulic pressure is also indicated on the system's display. The indications are expressed in pounds per square inch, and the full range of indications is between 0 and 4,000 psi. 3,000 psi is a normal value with the engine-driven pumps operating, as the pumps are rated to output pressure in this range. The pressure indicated on the system's display is measured downstream of both pumps. It is therefore an indication of the combined output from both the engine-driven pump and the electric pump for each system. This differs from the low pressure lights on the forward overhead panel, which source from pressure switches specific to each pump. A leak in any of the hydraulic systems will cause at least some hydraulic fluid to be lost from that system. Systems A and B are independent systems, so fluid lost from one system will have no impact on the other. We discussed earlier, albeit briefly, how the output piping from each system's reservoir is arranged. Each reservoir has two means by which hydraulic fluid may flow out of it: a standpipe and a port at the bottom of the reservoir. The standpipe stands up off the floor of the reservoir, such that the top of the standpipe stands around 20% the way up the reservoir. This is the same for both the A and the B system reservoirs. There is a crucial difference, however, between the two reservoirs that affects how vulnerable each system is to a hydraulic leak. The system A reservoir standpipe feeds the engine-driven pump, and the port at the bottom of the reservoir feeds the electric pump. If a leak develops in the system A engine-driven pump or its related lines, the reservoir will only drain as far as the top of the standpipe. At this point, the hydraulic fluid quantity indication on the system's display will read 20%. The remaining fluid in the reservoir will be sufficient for the electric pump to continue operating. If a leak develops in the electric pump or its related lines, the entire reservoir will drain and the fluid quantity will read 0%. The system B reservoir standpipe feeds the engine-driven pump and the electric pump. The port at the bottom of the reservoir feeds the power transfer unit. If a leak develops in either of the two pumps or their related lines, the reservoir will drain to the top of the standpipe. Because both pumps are fed by the same standpipe, this will result in System B pressure being lost. The System B quantity indication is calibrated so that it reads 0% when the fluid has reached the top of the standpipe. Once the fluid is drained below the top of the standpipe, it can only be used by the power transfer unit. So in summary, System A will drain empty if a leak develops in the electric motor-driven pump, and System B will drain empty if a leak develops in either pump. The power transfer unit, or PTU, provides an alternate source of hydraulic power for the leading edge flaps and slats if System B is depressurized. The PTU uses System A pressure to pressurize System B fluid. There is no transfer of fluid between the two systems. The PTU operates automatically when all of the following conditions exist. The aircraft is airborne, trailing edge flaps are set less than 15 but not up, and System B engine-driven pump hydraulic pressure drops below limits. It is triggered by engine-driven pump pressure because the engine-driven pump is about 6 times more powerful than the electric pump. This means that without the engine-driven pump, the B system is much less able to quickly extend the leading edge devices. When the 3 prerequisite conditions are satisfied, power goes to the PTU control valve, which opens to allow System A fluid into the PTU motor. The System A fluid turns the motor, which drives a pump. The pump receives System B fluid from the port at the bottom of the System B reservoir. The pump pressurizes this fluid, thus providing an alternate source of pressure to the leading edge flaps and slats. The PTU drives the leading edge flaps and slats to the full extend position. Note that the PTU is only augmenting the pressure supplied by System B to the leading edge devices. It therefore cannot work if fluid quantity in System B is too low, or for that matter, if pressure in System A is too low. We're going to deviate a little here and talk about the A320 family briefly, which has a very loud and conspicuous PTU. If you've ever flown on an A320 family aircraft, you've likely heard the PTU in action. The A320 has 3 hydraulic systems, and the PTU is used to even out pressure differential between the green and the yellow systems. It plays a much more important role on the A320, and runs more often as a result. The PTU on the A320 is much louder than that on the 737, so loud that it's very easily heard from the cabin, and sounds like a barking dog beneath the floor. It's common to hear the A320 PTU on taxi after landing if an engine has been shut down. It barks because it usually takes very little time for it to resolve the pressure differential between the two systems. The PTU cuts out once there is no longer a pressure differential. As soon as it cuts out, a differential begins to develop again. The PTU then activates again, and the cycle repeats. This causes the incessant barking that sometimes causes curiosity amongst the passengers. Let's get back to the 737 now. Because the PTU is only used under such specific and rare circumstances, it is very rarely operated. The 737 PTU is also much smaller than that on the A320 because it's only needed to power the leading edge devices. Its smaller size means that it also generates less noise, so you cannot hear it from the passenger cabin. We talk a little more about the PTU in the secondary flight controls lesson, and we also cover the landing gear transfer unit and the landing gear transfer valve in the landing gear and brakes lesson, so we will not discuss those systems now. We have discussed the A and B hydraulic systems in great detail, but we've not yet touched upon the standby hydraulic system. The standby hydraulic system is the third hydraulic system on the 737 and operates automatically or manually as a backup to systems A and B. It supplies alternate hydraulic pressure to the leading edge flaps and slats, both thrust reversers, the standby rudder PCU, and the standby yaw damper. Controls and indications for the standby hydraulic system are located on the flight control panel on the forward overhead panel. Similarly to the A and B systems, the standby system has its own reservoir which supplies hydraulic fluid under pressure to the pump. The standby system reservoir is mounted on the keel beam at the aft bulkhead of the wheel well. It is considerably smaller than the primary system reservoirs and contains only 3.6 gallons of hydraulic fluid. The standby system reservoir is linked to the system B reservoir by a fill and balance line, which serves several purposes. The three hydraulic system reservoirs are filled from a single port in the wheel well. A fill selector valve is used to direct the hydraulic fluid into the reservoir that needs to be filled. The system A reservoir is filled directly from the fill port, whereas the system B reservoir is filled via the standby system reservoir. One of the purposes of the fill and balance line is therefore to fill the system B reservoir via the standby system reservoir. It also serves as an overflow for the standby system fluid as it heats up and expands during operation. Crucially, it also transmits bleed air pressure from system B to the standby system reservoir to ensure positive pressure to the pump. The standby hydraulic system has a single electric motor-driven pump. This pump is rated at 3.7 gallons per minute at 2700 psi. This is the same output pressure as the system A and B electric pumps, but a considerably weaker fluid flow. Similarly to the A and B pumps, some of the fluid leaving the standby pump enters a case drain line and is circulated through the pump to cool and lubricate it. It then re-enters the reservoir. The actual pump motor is air-cooled by outside air flowing over it. It draws power from AC transfer bus number 2. The standby hydraulic system can be activated either manually or automatically by a number of triggers. There are 4 ways in which the standby system can be activated: 2 manual and 2 automatic. Controls and indications for the standby hydraulic system are located on the flight control panel on the forward overhead panel. Positioning either of the 2 flight control switches to standby rudder or the alternate flap switch to arm will activate the standby hydraulic pump. Whenever the standby hydraulic pump is running, fluid is supplied under pressure to power the thrust reversers. Fluid supplied to the standby rudder power control unit and the standby yaw damper and the leading edge flaps and slats is controlled by 2 valves: the standby rudder shutoff valve and the leading edge flap and slat shutoff valve. Setting either of the flight control switches to the standby rudder position opens up the standby rudder shutoff valve. This allows fluid to flow to and power the standby rudder power control unit and the standby yaw damper. Setting the alternate flaps master switch to arm, then selecting the alternate flaps position switch to down, opens up the leading edge flaps and slat shutoff valve. This allows fluid to flow to and power the leading edge flaps and slats. There are also 2 conditions which will automatically trigger operation of the standby hydraulic system: tripping of the main rudder PCU force fight monitor, or low pressure in system A and/or system B. Low pressure in the main systems alone will not automatically initiate the standby hydraulic system. There are a number of other conditions that must be fulfilled. Flaps must be extended, the aircraft must be airborne or the wheels spun up beyond 60 knots, and at least one of the 2 flight control switches must be set on. The force fight monitor on the main rudder power control unit detects opposing pressure between the A and B system actuators. If the force fight monitor is tripped, the standby system is activated automatically. It is a vital safety mechanism and deserves comprehensive discussion, but is a little beyond the scope of this particular lesson. We cover the force fight monitor in detail in the primary flight controls lesson. When the standby hydraulic system is activated automatically via either method, the standby rudder shutoff valve is opened. This routes hydraulic fluid through to the standby rudder power control unit, allowing the pilot to retain sufficient rudder control even when systems A and B have failed. The standby yaw damper system provides Dutch roll prevention, gust damping, and turn coordination for the standby rudder power control unit. We cover the yaw dampers in more detail in the primary flight controls lesson. Although the standby rudder shutoff valve may be opened automatically, the leading edge flaps and slat shutoff valve must always be opened manually when required, even if the standby hydraulic system has already been activated automatically. This is done by selecting the alternate flaps master switch to the arm position, then momentarily holding the alternate flaps position switch to the down position. The leading edge devices may then be extended using this switch. Indications for the standby hydraulic system are located on the flight control panel. The standby rudder on light illuminates amber when the standby hydraulic system is activated and the standby rudder power control unit is pressurized. The low quantity light illuminates when the hydraulic fluid quantity in the standby reservoir decreases to less than 50%. The low pressure light illuminates when the output pressure from the standby electric pump decreases below limits. This light is only armed when the standby pump has been commanded to run either manually or by the automatic triggers. The light is therefore inhibited when the standby electric pump is not selected on. Illumination of any of these three lights triggers a master caution and the flight control light on the captain's system annunciator panel. When discussing the consequences of fluid leaks in the A and B hydraulic systems, we discussed standpipes in those reservoirs which can help prevent total loss of hydraulic fluid depending on where the leak is. The standby system reservoir does not have a standpipe, so any leak in the standby system will result in reservoir quantity decreasing to zero. System B will continue to operate normally, however the System B reservoir fluid level will decrease to approximately 72% when the standby system reservoir is empty. The value is 72% as this is the level of the fill and balance line that connects the standby system reservoir and the System B reservoir. As fluid is lost from the standby reservoir, and its quantity decreases through 50%, the low quantity light on the flight control panel will illuminate, triggering a master caution and the flight control light on the captain's system annunciator panel. We'll finish up here with a lesson summary. The 737 features an impressive level of system redundancy throughout, and the hydraulic system is no exception. Even with complete failure of systems A and B, the aircraft may still be flown through manual reversion, which uses pure mechanical linkages to the elevators and ailerons. We gave a comprehensive overview of the standby hydraulic system, but there is still much ground to cover with regards to the rudder, the leading and the trailing edge devices. We felt it better to leave the details for the primary and secondary flight controls lessons, as they are much better placed there, along with coverage of the rest of the flight controls. In this lesson we covered an overview of the general principles behind hydraulic systems, an overview of the hydraulic system on the 737 Next Generation, hydraulic systems A and B, systems A and B fluid leaks, the power transfer unit, the standby hydraulic system, and standby hydraulic system fluid leaks.